In this question, we're comparing two gases. We have gas A, which is a molecular gas containing small, non-polar molecules that have dispersion forces between them. Gas B in this question is also a molecular gas. This time it contains large non-polar molecules that also have dispersion forces between them. So the difference between gas A and B in this question is the size of the particles. Gas A has small molecules, gas B has large molecules. So to answer our first two questions, which gas has the greatest particle volume? That's going to be gas B. Which gas has the strongest type of interparticle forces? Well, we're told both have dispersion forces, which are pretty weak. So we have about equal interparticle forces for these two gases. Okay, our next question is asking which gas would be expected to deviate most from the ideal. So it's useful to remember what ideal means. An ideal gas is one that has no particle volume. So the particles are basically take up no space at all. And it's one where the interparticle forces between the particles are zero. There's no force between them. So either having a large particle volume or having strong interparticle forces, those are going to cause our gas to deviate from being ideal. In this case, the difference here is the particle volume, and it's gas B that has a larger particle volume, and therefore gas B that's going to be more likely to deviate from the ideal. Next, we need to figure out what is the effect of this going to be? How will that affect the pressure of the gas compared to the expected for an ideal gas, and why? So our difference is we have a difference in the particle size, greater particle volume. So let's look at our options for our description of why our change is happening. Greater particle volume is in questions 3 and 4. So let's have a think about the effect of greater particle volume. If we look at our image, gas B has greater size of particles, and therefore the amount of white space left in that container is less than it is for gas A, because the particles themselves are taking up a large amount of that space. So that's going to be description 4. Greater particle volume decreases the space in which particles are free to move, increasing the number of particle collisions with the sides of the container. Because there's literally less space for them to move around in, they're going to collide with the sides more often. So option 4 is our description of why we have a change in pressure. Finally, we need to add in what would the change in pressure be? Well, if we have an increase in the number of particle collisions, that's going to be an increase in the pressure, because pressure is to do with the number and force of the collisions over the area of our container walls. Higher number of collisions means higher pressure. So we're going to have a greater pressure for gas B. Okay, lastly, we're looking at the conditions when this deviation would be less apparent. So what that means is the conditions when our gas would be more likely to behave like an ideal gas. So let's have a look at our options down here. We're talking about gas volume, so that's going to be either number 1 or number 2. Let's look at our drawing here. So for gas B, we can obviously see that our particles are taking up a significant volume of the entire container. Now imagine we decrease the pressure and we got rid of some of these particles, because decreasing the pressure kind of spreads them out more. Now we only have 3 particles in here instead of 5. That's actually increased the volume of the container relative to the volume of our particles. On the other hand, let's imagine we added some more particles in. This would be like increasing the pressure. Now we have 7 particles or 7 molecules in here instead of 5. We've actually taken up more of that space. So in this case, when we've added particles and got a higher pressure, it's like the volume of the container has decreased even more. So by having a lower pressure and having more spread out gas particles, we're actually making the combined gas particle volume less significant when it's much less than the volume of the container. So we're looking at option 2 for the description. If the combined gas particle volume is much less than the volume of the container, That would be when we have a low pressure because our particles are more spread out, there's more space between them. And so the fact that the particles are large has less of an impact because they're taking up less of the volume overall at a lower pressure. So sentence 2 is our explanation, and it's at a low pressure that this would be the case. So our gas is more likely to be ideal at a low pressure because our particles are more spread out, and so the gas particle volume is less significant because they're taking up a much smaller volume compared with the volume of the container.